Asymptote. I'm pleased to introduce or reintroduce to you Mikhail Mamaev, who's a new postdoc in our group. Michael grew up mostly in Toronto before doing his master's with Dodge Clark back when he was at McGill, going on to do his PhD with Anna Maria Ray, Gilla, and is now at Chicago. Well, sorry, is until a few weeks ago, but according to this, still at Chicago with Ash Clerk again and John Chang. Has also co-authored with Joseph, who's in here somewhere, there. Shares a lot of interest with many of us, so I hope that you'll all have many chances to interact with Michael over the next while. And join me for now in welcoming him.
Thanks, Ephraim, and hello, everyone. Thanks for coming. I've only been here for, I guess, 3 or 4 weeks now, but thus far, people I've had the chance to meet have been very warm and welcoming, so I'm grateful for that. But I think there's still a great many people that I haven't met yet, so to that, I look forward to try and look out and find you over the coming months, couple years. And what I wanted to talk to you about today was basically just dynamics of atoms and optical lattices. And now the broad overarching goal beyond all of this is just that we want to understand the quantum mechanics of atoms, both from a microscopic level for a few body details, and kind of eventually interacting many body physics as well. Now that sounds pretty generic, and so the platform we want to consider is one that I probably don't need to introduce to most of you, which is optical lattices, which is essentially a system that can mimic a more conventional solid-state crystalline lattice with some valence electrons hopping around. Instead, I have a crystal formed by light, where counter-propagating laser beams create a potential in which I can load individual neutral atoms. And you can engineer 1D, 2D, or 3D geometries. In this talk, I'm mostly going to be thinking about 3D, where you really have a 3D lattice and each atom is trapped in its own little cell. Now, of course, as we probably know, an optical lattices can be easier to control and measure compared to solid state because of the favorable spatial scales. 1 micron for optical frequencies instead of 1 angstrom. But before thinking about any sort of many body applications, and one of the earlier applications optical lattices were considered for is quantum sensing with something like optical lattice clocks, where people are probably familiar with this stuff, but just in case, the basic idea is if I want to do something like measure the energy difference of 2 internal states of an atom, E and G, which is crucial for things like electromagnetic field sensing, navigation, and maybe even dark matter searches, but don't ask me too much about that. I'm not a big dark matter expert. So if I want to do that, what I can do is drive the atoms with a laser. Now, not the laser is forming the lattice, but an additional laser drive of known frequency. And if I measure the detuning of that laser, I will be able to obtain the true atomic transition frequency. Now, again, I'll keep saying this a few times. You're probably familiar with this, but the way you can do this is with Ramsey spectroscopy, where you can use my laser to prepare a superposition of the 2 atomic states with a laser pulse. And for that superposition, the detuning of the laser acts as a sort of magnetic field. And that superposition will process along the equator of the Bloch sphere, and the accrued phase will tell us the detuning. So that's all pretty standard. Now, the thing is, if I have kind of this one-dimensional 2D or 3D lattice, but let's now just look at just one dimension, the laser that I use to prepare the superposition has a spatially varying phase, just a traveling wave with an electromagnetic phase e to the I kr, where k is the wave number of the laser. And now what that means is if I have the lattice with some spacing and the laser goes along the direction of the lattice, when I do a pulse and prepare a superposition, it'll have a different relative phase on each site. It might be e plus g on one site, and on the next, they'll have a phase e to the I ka with a lattice spacing, then 2ka, and so on and so forth. So essentially, it turns into something like a spin spiral instead of just a collective state of each atom in the same phase. Now, if the lattice is really deep and the atoms are isolated, of course, this doesn't have any effect. You can gauge that phase away. But for things like quantum metrology with optical clocks, it turns out that you actually don't want to go too deep of a lattice because you run into issues from light scatter. If you're tracking the atoms really deeply, laser light from your lattice will hit your atoms and kick them out, and that limits coherence times. Now, it's not a showstopper. Optical lattices, clocks have worked with that, despite that all the time. But if you really want to find something like dark matter, well, it might start being an issue. At the same time, you kind of don't really want to go too shallow. because then your atoms will start to tunnel around. And because they have this relative different phase, the spin and the position of the atoms are coupled. So it's a light-induced spin-orbit coupling, which can also dephase your Ramsey signal. And also going too shallow, there's other bad things that can happen as well. So in principle, and that has been studied in several experiments. So in principle, you want ideally to operate at some kind of intermediate lattice depth, for which we will have to understand the effects of the spin-orbit coupling, at least perturbative. But if there's one message I want to get to you throughout this whole talk, if I get through it, is that this spin-orbit coupling is not just a bug, it is a feature. Because we can use it to induce and then study non-equilibrium many particles in lattice for the purposes of quantum simulation, simulating a real material. So as an outline, first I'm going to tell you guys about some perturbative spin interactions that can emerge and be tuned by this spin-orbit coupling. Then I'll talk about applications of these interactions for creating entanglement, useful for quantum metrology. And if there's time, I don't know what the time scale is, but I'll tell you something a bit more fancy, some exotic constrained Hubbard models that can emerge in such a system. And I don't know what the policy is for CQIQC questions mid-talk. I'm personally okay with it. If you haven't, please go ahead. Okay, so to set the stage, the system we're going to study theoretically is a 3D optical lattice. It's going to be loaded by two flavor fermionic atoms. So these are fermions, state C and G, all in the lowest notional band. And we're going to consider geometry with lattices shallow along one dimension only. So it's really just a collection of independent 1D tubes. And we'll study one dimension for simplicity, but most of what I'm going to tell you can extend to 2D or 3D as well in a straightforward manner. And will hopefully be at near unit filling, so roughly 1 particle per second. Okay, so the way that we model this is, again, something you're familiar with, which is a Fermi-Hubbard model, where you've got nearest neighbor hopping of the atoms from one side to the next with some matrix element J. I apologize to any condensed matter theorists in the audience. Their tunneling is often called T. But here for us, T is time, so J is the hopping rate. Now, if I have two fermions of different flavors on the same site, they have an on-site Hubbard repulsion U. And we'll assume that that Hubbard repulsion is strong, so we're in the not insulated. Now, finally, I have kind of a laser that I use to create Ramsey superpositions. And this is basically just a Rabi drive on every lattice site with some Rabi frequency omega driving spin flips. This is hitting every single lattice site. And as I said before, we've got this spin orbit phase, which I'm going to write as e to the I j phi, where j is the site index, and phi is basically kind of the spin orbit phase per lattice site, which you can tune by controlling either the wave vector of the laser or kind of the angle it forms. And this physics induced from this sort of spin orbit coupling in this system has been explored in a ton of experimental works recently with naval platforms. I have 8 here, and I apologize if I've missed more because there's really so many, and a ton of theory work as well. Now, to be clear, what we're going to study theoretically is prepare to a pi-half pulse, assume that the Rabi frequency of the pulse is much stronger than kind of any other lattice dynamics. Prepare a pi-half pulse, it's a superposition that has this spatially dependent relative phase. Then we turn the laser off, set omega to 0, and then just evolve under the Fermi-Hubbard model. Unitary dynamics, no dissipation or anything. Okay, that's what we study. Numerically and numerically. Now,
sorry, I missed one. So what does omega control in the previous?
It's the Rabi frequency of the laser.
Just
that's all. We will turn it back on later. So yeah, that is worth. It turns out for this sort of system, it's convenient to make a basis transformation. Because I have this relative spatially dependent phase. What I can do is take my fermionic operators and basically unwind the spiral, gauge it away. What that means is instead of having a spiral initial state, I will now have a uniform initial product state, each atom E plus G. But the price the Hubbard interactions remain unchanged, but the price you pay is now the tunneling acquires a phase. Whether E atoms hop or G atoms hop, they have this E to the I phi or E to the minus I phi shown. But we're still in a non-insulating phase, so the effect of this tunneling should still be perturbative. And we basically want to compute what that is. Now, conventionally, if I didn't have any of this sort of spin orbit coupling, I can just say if I have one atom per site, strong on-site interactions. I say if I have an E atom, that's going to be a spin up, G atom is a spin down, and a spin with half degree of freedom. And the lowest order perturbative effect of tunneling is second order super exchange interactions. So we have two neighboring atoms. One guy hops to his neighbor. He cannot remain because it costs too much energy, so he just spends the night and comes back. And you can obtain from standard free flow perturbation theory that this is just a Heisenberg interaction of strength J squared over U with this form S dot S. And I can write it more explicitly. I apologize if this is well-known stuff, but it has a poly XX plus poly YY plus poly ZZ, or alternatively kind of a flip-flop term and an Ising term. Now, the grand state of this is anti-ferromagnetic for fermions and ferromagnetic for bosons, but I emphasize that we're really looking at non-equilibrium physics. And in the absence of spin orbit coupling, the Ramsey spectroscopy to be the first pulse would just prepare a pretty simple, somewhat trivial eigenstate of this Heisenberg Hamiltonian. Just an equal superposition to which nothing happens.
Help me understand why this is spin orbit coupling, these are in one dimension.
Yeah, so
in what sense is there any orbital motion?
yeah, I would say and apologize that this is kind of an abuse of nomenclature. It's really, you should just call it a spin position coupling.
Okay, not enough. Thank you.
I wouldn't have called it that myself back in the day.
Can I ask a related question? Because when I look at this, the first thought is just that when you're exciting them because of that relative phase, you're also changing the quasi-momentum. You're exciting some different quasi-momentum state. If you're not,
You can think that it's shifting the bands.
well, I guess this was my question. Are you assuming that you're in a sufficiently tight binding limit that doesn't couple the higher bands?
Yes,
Okay, because otherwise I would say it really does sound like spin orbit if you extend the band.
that would be even more interesting, but more complicated. It's more interesting, but we're not in that. Okay, so if we have spin orbit coupling, the SE2 symmetry of our Heisenberg super exchange interactions is broken. And you can show that the Heisenberg model we get sort of becomes a twisted Heisenberg model. I still have an Ising term and a flip-flop term, but now the flip-flop term inherits the spin orbit phase e to the IP. You can take that e to the IP and expand it out in terms of trig. You've got a cos phi xx plus yy plus my Ising term plus sine phi xy minus yx, which is a weird sort of Hamiltonian. Sure.
Because I thought that your spin orbit coupling is basically a phase position,
Okay, so
phase and the position.
yes.
So should I have phi, which depends on the J as well? Site dependent, JJ plus one.
No, it turns out no. When you make the gauge transformation, because we only have nearest neighbor coupling, it does not depend on J. If we had like further range interactions, there would be a J.
I think phi is already the phase gradient.
Yeah, so it's just phi by two.
Yes.
So it's a unique.
But you're right, if we had more levels or if we had like longer range, there would be a J. But anyway, yeah, so this is the Hamiltonian we get. And this contains different pieces that are in and of themselves rather interesting. The first two terms are technically what we would call an XXZ interaction, which is well known in condensed matter physics and relevant to spin magnetism, spin transport, even some exotic KPZ scaling diffusion properties, which people have looked at in optical lattices pretty recently, and especially entanglement generation. And that's the application we're going to be looking at further on. Now, the other piece of the Hamiltonian is called this xy minus yx sort of chiral term is called the Dzialojinsky-Maria DM interaction. Also shows up in condensed matter and it's relevant to topological properties of materials. And we get these fermion defects that form. Now, I'm not going to dwell on this. It's an interesting topic too, but I mostly wanted to highlight this because I always like drawing these cool, pretty pictures of the fermion too. Yeah, we won't focus on that in this talk. But the thing is, we kind of get both of these terms, the XXZ and the DM, showing up at once. And it's not a priorly obvious to just turn off one or the other. I could set phi to pi and then this guy is 0, but then I've fixed the anisotropy, kind of the ratio between the Ising and the xx plus yy terms for the rest of the Hamiltonian. There are some interesting properties of this whole model kind of all as it is that have been explored. People talk about Bethe phantoms and stuff like that in some of these papers. But it would be nice to just isolate, for example, the XXZ interactions, these first two terms, and still be able to tune the ratio between the coefficients. Because as I will show you, that is beneficial to entanglement generation that is useful. Now, one way to do that, which we'll explore, is basically to drive the system. Instead of just doing an initial Ramsey pulse, I keep my Rabi drive on throughout quantum dynamics. And study now kind of e to the minus IT, Fermi-Hubbard model plus the Rabi drive as well. But we asked, how does that tune the super exchange? Well, you can just do degenerate second order Schrieffer-Wolff and get the Hamiltonian, and that all works just fine. I'll show you in a moment.
Ask one question going back. So when you say that you're doing this Ramsey pulse, you're saying that's like doing some state preparation in the beginning.
That's right.
But then, so what is the statement about the Hamiltonian here? I was not sure what this means. So now when you're looking at subsequent time evolution of that particular state, it will evolve according to this.
That's right. That's
And that's after you do this transformation to
exactly. So if I didn't do the transformation, I have a non-uniform initial state, which is just a Heisenberg SQ symmetric Hamiltonian.
Okay.
Equivalently, I can unwind the spiral of the initial state and make uniform, but now I get a non-Heisenberg Hamiltonian.
And to what extent can I? So what I'm confused about is that the statement seemed to be that I have derived some effective Heisenberg model, but this. I'm still confused because you're starting with some initial state for which this is going to describe time evolution. So you're saying for time evolution purposes, this is a useful way to think about the spin physics and how.
Yes, but in principle, I'm always allowed to do that gauge transformation. And in that, after making a transformation, in that basis, I will always have this Hamiltonian. So it's not restricted to that specific initial state. It just happens to be convenient to go into that frame for that. Okay, yeah, so before, just doing mathematical Schrieffer-Wolff theory, I find it is intuitive to kind of consider the system in the case where the spin orbit phase is pi, so it's maximal. And in that frame, kind of in the lab frame, before making any gauge transformations, kind of my Rabi drive basically looks like e to the ij pi sigma x. Now, as we know, e to the ij pi is just -1 to the j, so it's an alternating sign. And the eigenstates of Pauli x are just e plus or minus g. Positive and negative energy. But because of this alternating sign, they will likewise alternate. So the positive energy eigenstate on one side might be E plus G, but on the next it'll be E minus G, and so on and so forth. And what we can do, and I apologize for yet another basis transformation, but that's kind of what you got to do here, is we can take these kind of dress states of the drive, kind of just eigenstates of the Rabi drive, as spin states in of its own right. So let's say I have a dressed spin up and a dressed spin down with positive or negative eigenenergy of the Rabi drive. And in that frame, in that basis, what that means is if I start with, let's say, a dressed spin up state in E plus G, when it hops, it stays as E plus G, and effectively flips its spin. So when I have this spin orbit phase of pi, it's as though when I hop, I flip from spin up to spin down, or vice versa, if from down I go up. What that means in the context of super exchange is if I have a super exchange process, like let's say two dressed spin ups, this guy might spin flip hops to his neighbor, he can't stay, plus too much energy comes back. That's an Ising term, but now the energy gets tuned by a factor of minus omega because he flipped from up to down. So the super exchange coefficient goes like J squared over U minus omega, or U plus omega if we were both down. Oh, by the way, this should be omega. I was telling you about the cursive PowerPoint bucket. This is one. On the other hand, flip-flop interactions, if I have, let's say, this guy spin flips and comes here, this guy spin flips and comes here, would not conserve energy at all if I'm driving strongly. Because this costs me minus omega for this guy, minus omega for this guy, so minus 2 omega. And if J is much smaller than omega, then this process is suppressed. So essentially for strong driving, we get an Ising model instead of the Heisenberg. And while I don't want to dwell on it, we have explored the use of such Ising models for generating cluster states, which are basically many-body entangled states relevant for measurement-based quantum computing, where you basically kind of apply all these interactions in parallel across the lattice all at once, make an entangled state, front load all your entanglement generation, and then just measure. Again, I won't dwell on it, but that is a particular thing that you could do pretty easily with this sort of setup. Now, so for phase pi, we get Ising. For no phase, we get a Heisenberg. As you can imagine, in between, we would get something in between. So if I have spin orbit phase between 0 and pi, we can still go to the sort of dress state picture, eigenstates of the Rabi drive. But now, when a particle's addressed spin hops, it can either flip its spin or conserve its spin, kind of with some hopping matrix elements that depend on the spin orbit phase phi. I have a cos phi over 2 and a sine phi over 2. And so, from this, you can show pretty straightforwardly that in this basis, my super exchange interaction becomes indeed an XXZ model with semi-anisotropy delta, which is controlled by kind of the on-site Hubbard U, the Rabi frequency, and the spin orbit phase phi. There's also the laser, I'm still Rabi driving, that term is still in the Hamiltonian. But because I've gone into the eigenbasis of the Rabi drive, that's just like a sigma z, so that can be used with the Hamiltonian. I can.
Sorry, I'm confused. Can you move to the previous slide?
Sure. This one.
Yeah, there. Yes. If imagine that my omega is much larger than j square over the u, which is exchange interaction scale.
Yes.
Then normally you don't have the exchange because omega is very large. Basically you're having a singlet. You have one state down one side, and then the exchange process completely suppressed. So I'm confused that when you take the omega much larger than the j in the second process, you just end up with Ising model.
You mean this process? So this process does scale. So this process is.
Yeah, I'm saying overall, like if I have the scale that you're supposed to compare is not the omega and the Hawking j, but it's omega with exchange interaction, which is the tj square over the u.
Yes, but if you have a process that is Ising-like, in principle, I start and come back to the same state. So the net
Right,
energy cost
But
would still be.
that exchange process is still has to be larger than your separation between the two, because in condensed matter physics is nothing but the atomic crystal potential. So if the potential between the two atom states are very far away, it's like atomic potential for us. So then when they are very large, then the exchange process is completely suppressed. But if they are comparable, then in general, you would expect to see a Ising plus the omega times that potential differences in the Hamiltonian. So
I think that is
naively think that you end up with Ising SCSC plus omega with an energy separation between the two, which act like the Zeeman field.
Oh, sorry.
So
You're
that's
saying that
what
there's
I'm
also
saying.
plus an Ising.
Yeah, I think it's like.
No, you're right.
There, in
That's
that energy scale that you're interested in.
You're absolutely correct. Here as well, there is the extra
Yeah.
Rabi splitting. I just didn't write it because I didn't use. My apologies. Yeah, that's right. I said that I have the laser drive here, but it commutes. The same also applies on the trees. Okay, but in principle, we now have an XXZ model whose anisotropy, which is what we wanted, we can't freely control. Here I have a plot as a function of the spin orbit phase for different kind of ratios to the drive frequency to the Hubbard view, and you can see even any anisotropy, which is good both for the purpose of simulating XXZ models using AML platforms, and as I will show you very shortly, for generating time. This is already something we were happy to find. Now, before talking about entanglement, I guess I should mention that we worked on some experimental verification of these models. There was an early experimental result, recent experimental result on kind of this anisotropic super exchange with the spin orbit coupling with Junyi strontium 2 experiment at Gillette. Now, they didn't do the laser dressing, they kind of didn't keep the Rabi drive on yet, so they just studied this twisted Heisenberg model. That has been looked at before by, I think, Wolfgang Ketterle at least, but here we were the first to see coherent dynamics that show up. And what they studied is basically the spin contrast. So, if I have my little individual spin on hats and I stack them together into a big collective spin that lives in a big Bloch vector, big Bloch sphere, the contrast is basically the length of that collective spin, which gives you the strength of your Ramsey sigma. And long story short, it worked. We were able to find good agreement with our theory predictions to the time evolution of the contrast under these twisted Heisenberg dynamics. Now, I should point out that that system was definitely not that close to unit filling of one particle per site. Normally, that's an issue for kind of these super exchange mappings, because if I have an empty site, I can just hop into that site at some tunneling rate J, which is much faster than the super exchange. So everything sort of gets washed out. In our case, the experiment had a pretty tight harmonic trap, which means the local energy differences between adjacent sites were big enough to suppress direct tunneling. So every particle is pinned in place regardless. If it has a neighbor, it can undergo super exchange. If it does not, well, basically just nothing happens. So this is one of those cases where, at least as far as super exchange is concerned, the harmonic trap did more good than harm. But yeah, that was pretty exciting to see.
Maybe back up and tell me what you mean by averages with last week. More than its efficiency.
Well, I guess
It's the actual experiment that you were showing next.
so. In principle, you start with all atoms kind of in the ground state. You to turn on your laser with the spin orbit coupling and do a pi-half pulse, which excites them all onto the equator of the block sphere. Then you turn your laser off and you sit for some dark time t, which is pretty long. You wait, and then you do another pi-half pulse to excite it into excitation fraction, and see how much you had left.
Okay.
Yeah, so this we were excited to see. And now, this maybe
So can you go back? So can you explain the result here? The contrast is a function of time, what is happening?
yeah, so in principle, if I didn't have any super exchange interactions, if I so for Ramsey spectroscopy, I process and acquire a phase, let's say delta t. If I make my laser resonance, make delta as small as possible, basically set it to 0, nothing should happen. So my contrast should start at 1 and should stay at 1 throughout the dark time and basically just remain that. If it does not, in this case, because of these kind of anisotropic spin interactions, which cause the contrast to decay over time as entanglement is built up between the particles. And there is some oscillatory dynamics, which tells us kind of the frequency, the strength of the super exchange interactions, which is what the experiment sought to measure. Yeah.
But the red curve is the theory and then dots of experiment.
That's right.
But the experiment is way more richer than the theory, right? You see-
Wow.
Actually,
See the scout now.
But there's a little oscillation, so there might be something hidden or beyond the what.
That is quite possible because, as someone mentioned earlier, you can have band excitation, which could have a faster oscillating envelope on top of the bare ground band physics, which is what this is, the theory curve. I mean, if you ask, is there more in there? Yes, I'm certain.
And how much of this decay would be because of the lasers firing for the
There, I think the coherence time is not a problem for dark times that they are probing here, because June has this amazing cavity locked super laser.
So in other words, is there an experiment showing this contrast not decay?
Okay, yes, you're right, in that there is an additional exponential damping factor, which they benchmark in the absence of the spin orbit coupling physics. But that gives a relatively small damping factor, I think it's like 10% or something like that, which is basically added to the theory. So it's accounted.
What's the temperature here in the experiment?
I remember it in nanokelvin. I don't know if I can do it in, it's like hundreds of nanokelvin. In principle, or one way to put it, we are definitely not using the film. So we were not that important. Cool.
I hadn't noticed until your discussion about Chinese laser, what the x-axis was.
Yeah.
Sometimes when you say long, or really remarkably long, that's
This one.
set just by the super exchange.
So this time, so this oscillation frequency is a super exchange. So it is a pretty small matrix element because you've only got an oscillation at 2 seconds. But they were able to measure coherent dynamics coming from it. So that I think they were pretty excited to see.
So, the red line represents your theory, right?
Yes.
I would like to know why, on the final part, so when that time is high, you have a large arrow. I mean, you have the.
Ah.
This is why.
So that leads to the earlier question of there is a finite additional overall coherence time kind of in the absence of any supernorbit coupling. And the error bar is basically the experiment had an error bar on that coherence time. So we take our theory prediction and multiply it by e to the minus the calibrated gamma t. But that gamma has an error bar, and which is just basically inherited by the theory.
And increase with the data, because I see that
Yeah,
when
that's
that time increase, your,
That's right.
okay,
But it's because we take the theory prediction and multiply it by the equals.
I see.
Any other questions? Cool. Okay, so I don't know how I'm doing on time, but we can definitely get at least through this one. I now want to talk a bit more on the theoretical side about, we measured these XXN interactions or these spin super exchange interactions, and we might ask, what can we actually do? Well, one thing we can do is for these parameter spectroscopy protocols, the way it works is you prepare superposition and you would measure the approved phase, but that superposition will have some quantum noise, as we know, that goes like h bar, which limits your signal. And the way you fix it, of course, is you take not one atom, but n of them, where n is as large as possible. If you stack them together into a collective Bloch vector, that will have some length signal strength n, but the quantum noise will go like root n. So your signal to noise ratio that you can achieve is roughly 1 over root n. So that's the standard quantum limit with non-entanglement particles. Now, if you have interactions, what you can do is, for example, squeeze the noise, kind of reduce the variance along the axis I want to measure at the price of increasing it versus in some other direction, for which you can show the ultimate possible sensitivity will instead be 1 over n, entanglement is used. This is the Heisenberg limit. And I apologize, the Heisenberg limit is not related to the Heisenberg model. Sorry to make I've had people confused about this in the past. But yeah, those are totally different things. Heisenberg did a lot of things. But yeah, so this is the best you could possibly do. Now, in general, you can characterize how well you perform above the standard quantum limit. You just non-entangled particles with the Weinland squeezing parameter, which is basically just the minimum variance along kind of the axis I care about divided by the spin length. So it's a noise to signal ratio. So smaller c squared is better. And the ideal is c squared is 1 over n, which would be the Heisenberg. Now, there has been a ton of effort in trying to kind of demonstrate this scalable improvement with entanglement with many platforms, many interaction mechanisms. You have Rydberg, dipole-dipole, cavity-mediated, photon-mediated, the list goes on and on. And these are just for the past couple of years, I think, these pictures, and you all see they have kind of some parameter that goes below 1 demonstrating an improvement. But I would say demonstrations beating state-of-the-art sensitivities like June's SR2 clock are still very much lacking. They've done better than their own non-entangled experiment, but one wants to do better than every other experiment. Now, turns out that the XXZ models we're talking about are useful for generating squeezing. And we can see that in a pretty simple way. If I just take my XXZ Hamiltonian and rewrite it as S dot S, a Heisenberg model, plus an Ising term with delta minus 1. Delta is the XXZ anisotropic. I've just rewritten it. Let me make an approximation. It's not true, but let me pretend for a moment that this interaction is not nearest neighbor, but all-to-all. Then this will look up to a factor like an all-to-all Heisenberg model and an all-to-all Ising model. Every spin talks to every other spin. And this latter is known as the one-axis twisting Hamiltonian, probably seen this before, which at the mean field level is just a collective rotation SZ that depends on the magnetization SZ. Now, the one-axis twisting model generates spin squeezing by simply taking, if I have a superposition, this is the equator of the Bloch sphere with some quantum noise. If I'm north of the equator, my magnetization is positive and I twist one way. If I'm south of the equator, my magnetization is negative and I'll twist the other way, so it's this shearing motion. And if you take that and you rotate it back to be vertical, I have indeed a squeeze state that I can use for metrology. I also have the Heisenberg term, but for a collective product state, that doesn't do anything. It's an acting state, so they just kind of does not affect the dynamics. Now, you can plot the Weinland squeezing parameter for the one-axis twisting model as a function of time. It's time evolution started from X product state. It reaches some minimum squeezing parameter 1 over n to the 2/3. It's not quite the 1 over n ultimate limit you can get with the Heisenberg limit, but it's pretty good. And I will say, just between friends, I don't think anyone has come anywhere close to this practically for any n bigger than like 3 or 4. N is in these experiments is tens of thousands, so that means. So, yeah, we're still very far away from that, but this is something that we would love to be able to achieve. Now, normally, of course, I cheated. Our interactions that we have are not all, they're nearest neighbor and they're 1D. If you have those kinds of XXZ nearest neighbor interactions, you can still get squeezing some amount, but it'll cap out independent of the particle number in it, versus just continuing to grow with that. But it has been shown, and this is a very active and I would say still somewhat debated field of research, that even these nearest neighbor XXZ interactions can behave kind of like collective all-to-all ones and generate scalable squeezing when they're close to the Heisenberg point of the anisotropy, specifically more on the easy plane side. So this is the anti-fermion, and this is kind of on this side. Now, there's been a lot of discussion as to why that is true, because it seems like a pretty cool thing.
Sorry, I've never heard of the Heisenberg point, that's delta equals.
Delta
minus.
equals.
So that's where your twisting term almost but not quite goes to zero.
Exactly. So I can't go to the point because then I don't have any squeezing dynamics. But it turns out if I come close, it's as though I act more collective. Now that's a weird thing. And in general, the higher dimension you are in, and the longer range your interactions, the more broad kind of this yellow region where things kind of behave collectively is. Now, why is that true? Well, there's been a long debate and a long discussion. People have talked about connections to Anderson's tower states and the underlying thermodynamic phase diagram of the XXZ model. Tomas Schilde and I think Norman Yao were thinking about it. I don't want to delve in too deep into why that is true, because that would probably be another 3 talks at least, which I'm not sure if I give all correctly. But the punchline is when you're close to the Heisenberg point, but not quite at it, you can have a scalable squeeze. And of course, in our case, we have an anisotropy that is controlled by these laser parameters, and we can come reasonably close to delta equals 1 if we want. There's a price to pay, of course, the closer you come, the longer it takes to generate your squeezing, but a reasonable trade-off can easily be found. Okay, so that's cool. One thing that we can do better by now, as I said, this works better in higher dimensions. So far, we've only been 1D, but let's not forget the fact that the optical lattice can have up to 3 dimensions. And one idea we can try is, I have these anisotropic XXZ interactions along 1 dimension of the lattice, say the vertical dimension, which is kind of the direction along which I point my laser. Now, an in-plane in the X and the Y directions, I can make the lattice shallower such that I have super exchange in those directions as well. But there, I don't have any laser. I don't have any spin-orbit coupling. All I'm going to have is Heisenberg kind of SU2 symmetric interactions. And what those can do is lock the direction of the spins together. So if I have 2 spins in plane that start pointing in the same direction, if they start to twist kind of in different directions from one another, there's an associated energy penalty. If these in-plane Heisenberg interactions are strong, that penalty will prevent the spins from kind of going opposite ways and lock each plane into kind of a big spin. And one can show that if I have, it's not a 3D system, but an effective kind of array of big spins, each interacting via XXZ, you can get better and more scalable spin squeeze. And we can show that just by a pretty simple calculation. Here, let me assume kind of the in-plane interactions are really strong and they're locked together in place as big spins. And let's say each plane has a spin S. So if S is 1/2, that means I have 1 particle in each plane. If S is 1, I have 2 particles in each plane. 3/2 is 3, and so on. And let me compute the achievable kind of the minimum spin squeezing as a function of total particle number n. You can see if S is 1/2, it's really just a 1D XXZ chain, spin 1/2. The squeezing gets a little bit better and it pretty much saturates. Doesn't go too far. If I have, spin 1s effectively, then it saturates at a lower value, and lower and lower and lower and lower, eventually following kind of this power law of n to the -2/3, which is precisely what one would get with an all-to-all Ising interaction. So in principle, this is a pretty exciting thing because we can just leverage kind of the properties of this 3D lattice to generate scalable spin squeezing with what are technically only nearest neighbor original interactions. Now you might probably ask, how do I actually know that kind of all the spins in each plane will really lock to one another? The answer is that's still being actively explored, but there's still strong numerical evidence. And even I think a recent experiment from Marcus Ryan, I apologize, I forgot the citation, which has shown that this sort of phenomenon actually happens. So yeah, again, if that would work, hopefully we'll see it in an experiment soon. It would be a pretty exciting thing. Because you can use these in situ interactions in this optical clock to make some squeezing, and then do Ramsey actually be the state of the art possible precision. Cool. So
what was N here?
So N, my apologize, N is the total particle. So if I have, let's say, S is 3 halves and N is, I don't know, 9 halves, that means I have 3 pancakes. But yeah, we have to measure our total resources for it. Okay.
I'm sorry, could you elaborate again, what do you mean the collective, why does spin act like a collect, what do you mean?
It means that I have in practice, I have this collisional nearest neighbor interaction. But the scaling of the metrological improvement I get from it when I evolve it dynamically is the same as I would get from an interaction that had every spin coupled to every other spin. Infinitely.
That you can push stuff, right, like it's.
Yes. Yes, and people, I would say, in the past year or so, have actually started to see at least hints of this experimentally, so it is a real thing. But as I said a couple slides ago, theorists are still debating on why this is true and what's true. Okay, let's see how much time I have left. I have to. Okay, good. Last thing I wanted to tell you guys about, if there's no other questions, is something a little bit fancier, which is basically going beyond spin models. I don't think this won't be too long. But so far the atoms we've considered to not move. It's a mod insulator. Let's suppose 1 particle per site, all the charge is frozen in place. But recall that in our dressed state picture, if I'm really driving the system with a laser, tunneling is as though it flips its spin. You have a particle pops, flip its spin, has to stay, and then comes back. And the matrix of it is j squared over u minus omega, because I flip from positive to negative omega. As you can imagine, if u is almost equal to omega, that picture is no longer valid. I no longer stay the night, I hop and I can stay forever. And what that means at this point is that the spin orbit coupling, kind of this relative phase I've applied, can enable genuine motion in the insulator. So it's not really an insulator or anything. And so what I want to do is to embrace that. Let's go to rest, set the Rabi drive equal to the Hubbard u and see what happens. Well, as before, let's start with the simplest case of spin orbit phase pi, which means if I hop, I have to flip my spin. If I have an atom sitting on its own, if it hops and flips its spin, it goes from, let's say, positive energy to negative, or negative energy to positive. And if I'm driving really hard, that process costs too much energy, so it can't happen. Lone atoms are pinned in place. If I have 2 neighboring positive energy atoms, let's say for positive Hubbard u, this guy can hop to its neighbor, form a double bond, costs minus omega plus u equals to 0. So this process can occur freely. 2 spin-ups can turn into a double bond or vice versa. 2 spin-downs cannot, because that'll cost it plus omega plus u. And if both of these are positive, that's still a ton of energy. So what this leads to is a weird sort of leapfrog-like motion where 2 spin-ups can turn into a double bond and then turn back into 2 spin-ups and then turn into a double bond and kind of leapfrog their way across the lattice. And that's the only kind of motion that can transpire. Now, you can write this down as effectively a constrained Fermi-Hubbard model. I'll spare you kind of the actual math for it, but you can imagine, okay? Where you have these single spin-ups, double bonds which can turn into 2 spin-ups, or spin downs, which basically act as a wall, because you can't get through them and you can't get past them, and they just kind of block off the lattice. Now, you can show kind of study the dynamics of a system for some simple situations, like let's say I start with 2 spin-ups beside each other, and they'll leapfrog either to the left or the right and spread ballistically across the lattice. And you can see that. I could also consider, let's say, 3 atoms spin-ups beside each other, and you might imagine 1 stays and 2 leapfrog away. But in practice, it turns out to be more complicated than that. Actually, more than 2/3 of the atoms end up staying behind, because as it turns out, they can minimize their kinetic energy by remaining close to one another. When they're all beside each other, there's 4 possible moves they can make, and when they're far apart, the leapfrog thing can only make 2 moves. So kinetic energy minimization dictates that they will actually kind of have a self-bound state and bind themselves to each other. And you can show that this actually is a parity effect. So 4 atoms will spread out, 5 will stick together, 6 will spread out, 7 will stick together, and so on. Just pretty cool to see. And if you want to be really fancy, you can even study scattering properties, like start with a pair of spin-ups. Okay, this is just a pair of spin-ups spreading out, leapfrogging. Or I could start with a pair of spin-ups near another spin-up that's kind of some distance away. So the vertical axis here I should have set as time. And this is the lattice site index. So the leapfrog propagates towards a single line, kind of scatters off of it, and some amount gets through and some amount gets bounced off. And it turns out you can even analytically calculate how much will get through and how much will pass in these constrained sorts of models. Now, I'm not going to dwell on these topics in too much detail, but in principle, these constrained hopping models can exhibit what's known as quantum scarring, which is basically a lack of equilibration depending on what initial state you start in. Now, that's probably pretty obvious just from seeing all these constrained hopping rules. But there are also connections to fracton physics, which in the most layman-ish of terms, is basically, as we've shown, particle motion that is contingent on the presence of other particles. Fracton because, it's fractional motion. You need 2 particles to be able to move, so 1 particle can only happen.
Why does the troubling doublons hit the third single and not create this 3 atom bound state? Why does this happen?
Because in principle that would cost energy, right? So the energy conserving process is to bounce off.
Oh,
It's you can actually model this sort of thing as a single particle problem scattering off of us. And that's where you get analytic calculations. And I won't dwell on this, but you can also use this kind of constrained sort of motion, rules on hopping, to generate entanglement in the form of tests. Ask me about that later. I don't actually it. So yeah, this is pretty cool to see. And I should say that was all for spin orbit phase pi, but you can also see the effects of such a resonance for spin orbit phase less than pi. For instance, I could prepare a state of all dressed spin-ups. And that's not the same as the initial state in Ramsey spectroscopy, but take my word for it, it's still a pretty easy thing to do in an optical lattice. There's still going to be some matrix element that kind of forms these doublons resonantly. And you can see that near omega equals to u, the population will deplete as a function of time. So that works. So it's not like a weird quirk of phi equals to pi only. But I should point out that there's also other resonances as well. For instance, I could have omega equals to u over 2 and have 3 spin-up atoms. This guy hops and forms a doublon, and then this guy hops and forms a doublon, and I get a resonance. This is similar to what you would find often in flow caves. All right, and of course, numerically, you can observe the presence of these different resonances. Let's say omega equals to u over 1, u over 2, u over 3. Just start with all atoms in dress spin up and track how many of them stay that way. If I'm not at a resonance, they'll all start spin up and stay spin up because energy is conserved, nothing happens. And at these different resonances, you decay and settle to some long time non-equilibrium average, which as it turns out, you can even predict just by doing kind of a microcanonical average combinatoric sum of kind of the different states you can reach according to the allowed hopping rules for a given resonance. And this is not unique to this particular initial state. In general, just you have this resonant physics that shows up kind of breaking your super exchange at certain points. Okay, and one last comment. This is only one slide because I don't want to get into this too deep, but as you can imagine, you can extend these ideas to more than 2 atomics, to atoms with more than 2 internal levels as well. For instance, alkaline earth atoms have a nice SUN interaction signature with only 1 interaction parameter. But you can do this with different scattering lengths too. You can play the same game, turn on a laser drive with spin orbit coupling, go to some dress basis with some eigenstates of the drive, and now have a bunch of different possible hopping processes kind of mediated by the presence of this spin orbit coupling. And once again, you can track these, prepare some dress states and see how many of them remain after the quantum dynamics of the system. And now you'll find a whole forest of different resonances that show up in 1, 3/4, 3/5, 1/2, 2/7, and so on and so forth. So yeah, that's pretty cool to see, but by now, don't worry, I'm almost at the end here. There's a question we should ask is why should we study all these complicated Hubbard models? Besides the fact that they're cool. Well, one possible connection is that you can take these, let's just go back to 2-level atoms, you can take these two level, 1D lattice, two spin states, and treat it as a ladder. Where the x direction of the ladder is the lattice direction, and the y direction of the ladder is kind of my spin states. And you can show that this spin orbit coupling phase is basically just a magnetic field piercing through the ladder. If a particle takes one look out of this ladder and pops all the way around, tunnels get laser excited, tunnels gets de-excited to pick up an overall phase feed. So I've got a 2D strip pierced by a synthetic magnetic field. And of course, if I had more than two internal levels, I'd have a more than two-leg ladder. So why is that interesting? Why did I only bring this up at the end? Well, in principle, that means you could try to find connections to the possibly fractional quantum Hall effect using these cold atom simulators. There's even been some recent work by, I think, Marcus Greiner and Leonardo Filani trying to explore this sort of thing and the effects of interactions. Now, when we saw these sorts of fractional peaks, we might have immediately thought, okay, is this quantum Hall? Absolutely not. This is energy conservation with a fancy bow tie on it. But one can show that similar sorts of approaches can be done to these models with more kind of realistic quantum Hall relevant interactions. And this microscopic approach of going to some dress spaces and looking for resonances, and from that trying to extrapolate to many bodies, which is pretty cool, I think, to explore. And finally, last comment, you could also use these sort of correlated tunneling processes, like one particle hops and the other one has to go next, to study lattice gauge theories for simulating quantum chromodynamics or something like that. Those are generally very hard to encode because a particle has to hop with another particle that hops. But it's something you can do with this sort of spin orbit path, and people have explored it. Okay, so with that, I think, I guess I should comment, the experiment, Jeannie's experiment was also able to at least find this resonance that I was telling you guys about. They didn't tune the Rabi frequency, but they kind of slid their cloud across the harmonic trap. And in places where the local potential energy matched the Hubbard U, they saw increased signal strength. So they at least found the resonance. Hopefully, there's some cool stuff that will come out of that. Okay, so with that, I think I want to wrap up. Hopefully I've convinced you that this laser-induced spin orbit coupling offers opportunities for anisotropic spin interactions, entanglement generation, and even this weird kinetically constrained physics as well. And I think you can gain a lot of intuition from the microscopic picture. And as some possible future outlooks, you can think about bosonic or free space analogs of these sorts of models. In fact, spin orbit coupling in free space, I would say these were originally started. You can also think about lattices with frustrated geometries, which people have been thinking about too, and maybe delve deeper into the ground state phases of the Hubbard models, maybe even in 2D or 3D. Okay, I think that's all I wanted to tell you guys, and thank you for listening.